नमस्कार बच्चों, मेरा नाम धन्या और हम लोग ग्रेड 11 केमिस्ट्री का सेकेंड लेसन देख रहे हैं जिसका नाम है एटॉमिक स्ट्रक्चर। एंड टुडे वी विल बी लर्निंग अबाउट बोर एटॉमिक मॉडल और बोहर एटॉमिक मॉडल। ओके, नाउ Bohr made certain postulates about the atom. Okay, so he considered atom to be a ping pong ball. Okay, and just like Rutherford, Bohr also suggested that atom has a center part called the nucleus. Okay, so the first postulate, Bohr made certain postulates. So atom can be considered as a ping pong ball with the central part called the nucleus. So atom has a center called nucleus, just like Rutherford. Okay, and just like Rutherford, Bohr also suggested that electron, I will represent electron with E with a negative sign. Okay, so electron revolves only in fixed circular orbits. Okay, so Rutherford had suggested that electrons revolve around the nucleus in circular orbits, but Bohr suggested the electron revolves around the nucleus only in certain fixed orbits with fixed energy and fixed velocity. So the electrons revolve only in fixed orbits, okay, with fixed energy and fixed velocity. So that means they cannot be anywhere around the nucleus. They should be in certain orbit and revolving with certain amount of energy and certain amount of velocity, or the fixed velocity. Now, what type of orbits the electron revolve around? So that is suggested in something called quantization condition. So quantization condition. Now, quantization means available in small amounts of fixed quantities. Okay, so electrons revolve. We saw that electron revolves only in fixed orbits with fixed energy and fixed velocity. Okay, so what is this quantization condition? Is that the electron revolves only in those circular orbits. Okay, so they revolve in circular orbit, yes, only in those circular orbits in which the angular momentum, this is the condition that was suggested. Angular momentum, which is represented by L, okay, is an integral multiple of h by 2 pi. Okay, so integral multiple of 2 pi, h by 2 pi, where h is a constant which is called as Planck's constant. This Planck's constant will be used in numericals, okay? So it has a value, it will be discussed later. So the electrons revolve in those circular orbits in which this condition is met, where angular momentum is a whole number multiple or an integral multiple of h by 2 pi, okay? So that means L is equal to nh by 2 pi. It should be whole number, not a decimal. So n can be 1, n can be 2, n can be 3, etc. Okay, but n cannot be 1 by 2, no. N cannot be 3 by 4. So basically n cannot be decimals. It should be a whole number or an integral multiple of h by 2 pi. Okay, now So we saw that electron revolves in different shells. Okay, so this is the nucleus. The electron revolves in different shells, in which the angular momentum is a whole number multiple or an integral multiple of h by 2 pi. Okay, and we saw that n values can be 1, 2, 3, etc. Right. So if n value is 1, it represents the first shell. This is the first shell where n is equal to 1. When n is equal to 1, it is called the K shell. When n value is 2, this is the second shell. It represents the second shell, and it is the L. The shell number is 2, and it is called the Lth shell. Okay. When L value is 3, sorry, n value is 3, it represents the third shell, and it represents the next shell, which is M. So K, L, M, N, and so on, depending upon the n value. Okay, so the angular momentum should be a whole number or an integral multiple of h by 2 pi. So if n value is 2, angular momentum will be what? 2h by 2 pi. If n value is 3, angular momentum will be 3h by 2 pi, and so on. Okay, so now coming to angular momentum, which is represented by L. Okay, now angular momentum L, maybe you would have studied in physics that it's a vector quantity. So angular momentum is represented by R cross P, where R is the radius and P is the momentum. And you know momentum is also given by mv. Yes? So we can also write this as R cross mv. And you know that the momentum is given by mv sine theta. Right. So if it's a vector quantity, so rmv sine theta. And this sine theta is nothing, theta is 90 degree over here. So we write it as rmv sine 90. And you know sine 90 is 1. So rmv times 1. So angular momentum L is given by rmv. Okay, so we also know that the angular momentum is given by nh by 2 pi. We know the two relationships, right? So equating both of them, we write it as rmv is equal to nh by 2 pi. Okay, and this is Bohr's quantization condition. So what is the Bohr's quantization condition? RMV or MVR, rather I'll write it as MVR, easy to remember that way. So MVR is equal to NH by 2 pi, which is Bohr's quantization condition, where H is a constant, which is called Planck's constant, and I told you it has a fixed value. 6.63 times 10 raised to minus 34 joules second. Most of the time, the values are mentioned in the question paper, but better just memorize it for if in case it's not mentioned. But usually they mention it, okay? And I told you a lot of numericals are given where you have to use this Planck's constant. Okay, so what is Bohr's quantization condition? MVR is equal to NH by 2 pi. Okay, so this was the third postulate. Okay. Now, the next postulate was regarding the circular motion of the electrons. Okay, so Rutherford had already explained that while revolving, when the electron revolves around the nucleus, the circular motion is converted into centripetal. The circular motion. The next postulate is about the revolving of electrons around the nucleus. Okay, now this electron is moving around the nucleus in a circular path. Okay, and you also know that if there is a negative charge and a positive charge, there is attraction, and this is called as electrostatic force of attraction. And when the electron is revolving, the circular motion, if any particle has a circular motion, the force that is there is centripetal force. The force that's there is centripetal force. So the electrostatic force that is there is converted into centripetal force. So this was explained during the Rutherford model also. When the Earth is revolving around the sun, there is gravity between the Earth and the sun. So that gravitational force is converted into the centripetal force. So similarly here, the electrostatic force of attraction that's there between the electrons and the nucleus, it is converted into centripetal force. So Fe, E means the electrostatic force that will provide the necessary centripetal force, or rather electrostatic force is converted into centripetal force, or electrostatic force provides the necessary centripetal force for the electrons to revolve. That's why the electron does not fall down into the nucleus. Okay, now moving on further. We just saw a condition. Electrostatic force provides the centripetal force, or electrostatic force is converted into centripetal force. Now, suppose we have two charges, Q1 and Q2, that is separated by a distance r. Then, because electrostatic force of attraction means it is between charges, so electrostatic force of attraction is given by 1 by 4 pi, this is a formula, 4 pi epsilon naught Q1 Q2 by r square. Okay, and 1 by 4 pi epsilon naught is a constant, yet a constant. Q1, Q2 are the charges, and r is the radius between the charges, or the distance between the charges. Okay, suppose a particle of mass m is revolving with a velocity v and in a circular path. Okay, so whenever there is a circular path, the force is the centripetal force. So Fc, let Fc be the centripetal force. So the centripetal force Fc is given by mv square by r. So whenever a particle with mass m and velocity v is moving in a circular path, the centripetal force is given by mv by r, where Fc is the centripetal force. Now we just saw that as electrostatic force is converted into the centripetal force, okay, so Fe is converted into Fc. Okay, so In this case, this is the electrostatic force of attraction. Okay. Now, this is Fc. I'm writing it as mv by r. Okay. Now, this is equal to Fe. Okay. Now we have to substitute the value of the charges in Fe. Okay. Now we will talk about the electron. This is the electron with a negative charge moving around the nucleus. Now, students, you know that electrons have a charge of a negative charge, right? So, and inside the nucleus, we have the protons, right? So this part I'm just rubbing off. I need some space here. So you have the formula here, right? Okay, students. So this is the electron revolving around the positive nucleus. Okay. Now, how many protons are there inside the nucleus? We know that the number of protons is equal to number of neutrons. Sorry, number of protons is equal to number of electrons. Now, the number of protons is represented by what? Atomic number Z, right? So the number of protons is equal to number of protons is equal to the number of electrons, right? Now, if the charge, you know that the charge of electron is -1, and it is also represented by -e. And the charge of proton is equal and opposite to that of the electron. It is represented by +1 for proton. Okay, so in this case, we will represent the charge of nucleus as Ze. Why Ze? Because if the atomic number is Z, that means there are Z number of protons. So Z number of protons times what is the charge of the proton? +1. It is also represented by E. So I'm taking it as Ze. Okay, so this is for protons. And this one is for electron. Okay, so why Ze? Because there are Z number of protons as the atomic number is Z, and times the charge. Charge is +1 or E. I'm taking it as E. Okay, so substituting the value over here for the formula of Fe equals 1 by 4 pi epsilon 0. The charge of electron is E. I'm representing it as E. I'm not taking the sign, I'm just taking it as E. So just to keep it uniform, I'm taking the charge of the nucleus as Ze. Okay, and the charge of electron is E. I'm not taking the sign now. Okay, so times Q1, Q2. Q1 is, let it be of electron, and Q2 be Ze by R square. This is the electrostatic force of attraction. For the electrostatic force of attraction. Now, we already know Fc is equal to Fe. Right? So we have to equate both of them. So I'll write it over here. So students, we already know that when the electron is revolving around the nucleus, the electrostatic force is converted into the centripetal force. The value of centripetal force is mv square by R. The electrostatic force of attraction is given by this value, 1 by 4 pi epsilon naught Q1 Q2 by R square. Now here what did we do? We found out the charges Q1 and Q2. Q1 and Q2 are general values, so we have to substitute the value. Q1 and Q2 are the charge of the electron and the positive nucleus. So charge of electron, I kept it as E. Okay. I didn't take the sign, although it is -1. I just kept it as E. And the Q2 is the charge of the nucleus. Inside the nucleus, we know that the protons are there, right? Now, the charge of each proton is +1, or it is also represented by +E. Okay. Now, how do you know the number of protons? By the atomic number. The atomic number, suppose it is Z. So Z times the charge E. Okay, so that will give you the charge of the nucleus. So I'm going to substitute the values over here. So Fc is over here. I have already substituted here. Okay. Is equal to Fe, that is 1 by 4 pi epsilon naught EZE by R square. I equated both of them, and this I put it in a box. So this is the condition of Bohr, that when the electrons are moving in a circular orbit, the electrostatic force of attraction is converted into the centripetal force that keeps them revolving. Okay. So this was the fourth postulate. So you must remember this formula, because sometimes calculations come from this part. Okay, so if the charges are mentioned, no worries at all. Okay, so here you have to take both the charges without the sign. Okay. Now the fifth postulate of Bohr was that while revolving in a particular orbit, the electrons do not lose or gain energy. Okay, so that means the energy of an orbit is fixed. So while revolving in a particular orbit, electron does not lose or gain energy. Okay, so that means energy of an orbit or a shell is fixed. Each orbit has a fixed amount of energy, and electrons cannot be anywhere. Like if this is the nucleus, this is the first shell, second shell. So they can only be there in these shells. They cannot be there anywhere between them. Okay, and each shell has a fixed amount of energy. That's why he called them a stationary energy level. Now students, the next part of the lesson is very important because it involves calculation of radius, velocity, kinetic energy, potential energy, and total energy. Okay, and a lot of formulas will come up. Okay, and these formulas are also very important. Sometimes the questions are very direct and you can solve it very easily. Okay, but just to derive the formulas a bit so that in between, if you forget the formulas also, you can derive it very quickly. Now, students, you just learned that the centripetal force, the angular momentum, is an integral multiple of nh by 2 pi. Okay, this equation you learned, right? Now you also learned another equation where the centripetal force is equal to electrostatic force of attraction, mv by r. These two formulas you just learned, right? Now this I'm putting it as equation 2. Now, if I square equation 1, this is equation 1, okay? If I'm squaring, so I'm going to find out the radius, okay? Here I'm going to calculate the radius of different shells. Okay, now These are the two equations you know. I'm going to square equation 1 and divide by equation 2. Okay. So if these formulas are given, it is very easy to find out the radius. If they ask you the radius of different shells, it's easy to find out. Okay, so I'm squaring equation number 1. So that gives me n square h square by 4 pi square is equal to mvr square, right? And I also have to divide by equation 2, which is ZE square by 4 pi epsilon naught ZE square by R square equal to MV square by R. This is equation number 2. Okay. Now, if I have to if the terms are coming as common, I can just cancel certain terms. So after all these cancelling things, I come to this value, n square h square by pi times epsilon naught by ZE square equal to m r square times r. Okay, so here also I have a few things which I can cancel. Okay, there are few common things again which I can cancel. For example, this r square and this r square I can cancel, right? So after all those, the simplified version is r is equal to n square h square epsilon naught by pi m ZE square. This is the radius of the nth shell. Okay, so you can substitute the different values of n and you get the radius. So this is very important, student. Okay, so if a numerical is given, you should be able to find out. Okay, so n is the shell number. Okay, and epsilon naught is a constant which is called as permittivity in free space. Permittivity of free space is just a constant. They will provide the value. Okay, Z is the charge and pi is the constant, you know that. And mass, m is the mass. Okay, they would mention the mass. Okay, and E is the charge of the electron. Okay, so this is a very important formula that you must remember. Okay, now from this formula, I'm just rubbing this part, okay. From this formula, I'm just accumulating the constant things together so that it's easy to remember. So radius of the nth shell, so h is constant, epsilon naught is a constant, pi m e square. All constant things, okay, n square by z. So this is a constant. This whole thing is a constant. Okay. Now, this whole thing is a constant. Now, after putting the values of all these, the radius comes to 0. This you must memorize, 0.53 times n square by z Armstrong. This is a very important formula, students. So in the exam, if you're able to remember this, you can solve the question very easily, where n is the shell number. So you just have to check the shell number given in the question, and z is the atomic number. Okay, because the mass of the electron, charge of the electron, everything is fixed. Okay, so this is the radius of the nth shell. Okay, so this is a very important formula. So n is the shell number and z is the atomic number. So this is the shortcut formula by which you can measure the radius. Okay, so let's do a question. You have to remember this formula. Okay. Okay, so I'm just keeping the formula as it is. So over here, I'll keep it as it is over here. Rn is equal to 0.53 times 3 times n square by z Armstrong. Okay, and you know what does n stand for? What does z stand for? Now, question number 1, find the radius of first, second, and the third shell of hydrogen atom. Okay, so you know the formula, you know which atom it is. So for hydrogen, the first shell R1 is equal to 0.53 times. The first shell n value is 1. Atomic number Z for hydrogen is also 1. So 0.53 Armstrong. Second shell, 0.53 times n value here is 2. So 2 times 2 is 4 by 1. Z doesn't change. It's the same atom after all, hydrogen. So whatever value you get, you will express in Armstrong. Third shell, 0.53 times 3 square by 1 equal to whatever value you get, you will express in Armstrong. So if a simple question comes like this, the direct application of the formula. Okay, but in case you forget this formula, you can just quickly derive it. It doesn't take much time. Okay, so this is one important question. One more question. Which of the following will have the same radius as the first shell of hydrogen? We just saw the first shell of hydrogen atom. The first shell of hydrogen atom. The first shell of hydrogen atom. We just found out 0.53 Armstrong. Okay, so instead of giving you this value, they just said which of them. I have not given you the choices. So these are your choices. N is equal to 2 lithium. N is equal to 2 beryllium. Okay. N is equal to 2 helium. and N is equal to 3 helium. Okay, so instead of giving this value directly, they have said as the radius of the first shell of helium. So this hydrogen, sorry. So this is the first shell of hydrogen. So you have to choose which of them will be having the same as 0.53 Armstrong. Okay, so the first one is lithium. Lithium, the second shell, right? 0.53 times N value is 2 times 2, 4 by the lithium, the atomic number is 3. So this doesn't give this value, right? Second one is for beryllium. 0.53 times beryllium is Z is 2. So 2 times 2 is 4. Sorry, the Z value is 4. Sorry. This is 4. So 0.53 Armstrong. So this is one of our right answer. But we have to check C and D. What's the story about C and D? Okay, so C and D. C. Helium is 2. Z is 2. Okay, so 0.53 times 4 by 2. No, this is not coming to 0.53. The last one. 0.53, this will definitely not come because this is 3 square, that is 9 by 2. So what is our answer? D is our answer. So these type of comparative questions might come. Okay. So okay, students. Next, we would be calculating the velocity of the electron in different shells, okay, or velocity of the electron in an orbit. Okay, we already know Bohr's quantization condition, MVR is equal to NH by 2 pi, right? Now, here we already know the value of radius, we already calculated a while ago. So I'm just substituting the value of R as N square, H square, epsilon naught by pi m z e square. So this is the value of R we just calculated, equal to NH by 2 pi. Okay. Now when we cancel the common terms, the value of velocity in the nth shell, okay, because we have used n. So nth shell comes to ze square, okay, ze square by 2h epsilon naught n. So this is the velocity of electron in the nth shell. Okay, so same like the previous one, I just accumulating the common terms, equal to E square by 2h. I'm just accumulating the constant terms, okay? 2h epsilon naught. The charge of the electron is constant, epsilon naught is constant, the Planck's constant is constant, okay? Times, what will change is the atomic number and the shell number, okay? When you substitute the value, there is an easy way to remember. It comes out to be, this has to be remembered, 2.18 times 10 raised to 6 times Z by N meter per second, which is very important so that you can use it directly. Okay, so they substituted the value for these and they found to be 2.18 times 10 raised to 6 Z by N, where Z is the atomic number, N is the shell number. Okay, so if I say the speed of hydrogen in the first shell, And how do you calculate? We just have to substitute the value. Hydrogen, the Z value is 1, N value is 1. So the speed of hydrogen in the first shell is 2.18 times 10 raised to 6 meter per second because it is speed. Similarly, you can calculate for different atoms with different shell numbers and different atoms with different atomic numbers. Okay. Okay, student. The next term that we would calculate is the energies of electrons. Okay. Now, electrons, you know that it's in a constant motion around the nucleus. And because it is moving, it has kinetic energy due to motion. And also, because there are opposite charges there, it also develops a certain amount of and also they also develop a certain amount of potential energy because there is a difference in charges. There is opposite charges there. So they develop a potential energy. Okay. So when positive and negative charges are around each other, they develop potential energy. First, we will calculate the kinetic energy. Okay. No. Now, kinetic energy is given by half mv square. Now, we already calculated the value of V a while ago. It is given by ZE square by two H epsilon naught N, the whole square, because the formula there's a whole square. Okay. So, which is equal to, so we will just remove the bracket M Z square E raised to 4 by 4 H square epsilon naught square N square. Again, all the this will come to be 1 by 8 m z square e raised to 4 by h square epsilon naught square n square. Okay. Again, assembling all the common terms, the kinetic energy comes to m e raised to 4. I'm assembling the common terms, okay, or the constant terms, sorry. H square. So this is the constant terms, z square by n square, where z is the atomic number, n is the shell number. So the kinetic energy comes to 13.6 z square by n square electron volt. So this is the formula for the kinetic energy. So you just have to substitute the atomic number and the shell number. You will get the kinetic energy. Okay. Now, students, we already discussed that when there are opposite charges involved, whenever there are opposite charges involved, there is also a development of potential energy. Okay. Now, suppose we have two charges, Q1 and Q2. So the potential energy PE is given by 1 by, just like the electrostatic force of attraction, 1 by 4 pi epsilon naught Q1 Q2 by R. Okay. So 1 by 4 pi epsilon naught. The charge of the electron is minus E. So here we take into consideration the charges. Okay. And Q2 will be ZE. I already explained that nucleus means it is made up of protons. And the number of protons can be the number of protons, how do we know? By the atomic number Z. And how many protons are there? Z number times the charge, which is positive. Okay, because the charge of the proton equal and opposite to that of the electron, or vice versa. Okay, so over here, what we do is minus Okay, student, we already know the value of R. Okay, it is n square h square epsilon naught by pi m ze square. This is the value of R. Okay, so we substitute it over here. So when we substitute 1 minus, there's a minus, I just took this minus out. 1 by 4 pi epsilon naught ze square pi m ze square by n square h square epsilon naught. So what did I just do? I substituted the value of R. Okay, so this is by R, sorry. So students, this is the value of, this is the potential energy that I got. Okay, so this I'm just, this part I'll just drop. This is the value of potential energy I got. Okay, so here there's an R and we already know the value of R a while ago, we just derived it. Okay, and I substituted the value of R. So when I substitute the value of R, I got this and I can cancel the common terms, right? So here I can cancel the pi. I can cancel it comes to minus m z square e raised to 4 by 4 epsilon naught square h square n square. Okay, so I got this value. Now, in order to, we also have an expression for kinetic energy just a while ago we derived. Don't worry with the long calculations and all, you will be given a shortcut formula. So in case you forget, this is for that, okay. So we just derived the kinetic energy formula, me raised to 4 z square by 8 h square epsilon naught square n square. Okay, so is this similar to this? This value, this potential energy equation, is it similar to this? It is similar if we multiply the numerator and the denominator by 2. When you multiply it, we get an expression like this. Minus m z square e raised to 4 by 8 times 2 by 8 epsilon naught square h square n square. Now when I compare, suppose this is equation 1, that is for potential energy. When I compare this equation with the kinetic energy term, is it appearing to be similar? It appears to be similar, right? So what I'm going to do is, I'm going to gather the common terms together, okay? I'm going to gather the common terms together so that it's easy to identify. So potential energy equal to minus m e raised to 4, just to make calculations simple, that's why. E raised to 4 by 8 epsilon naught square h square, okay? And z square is not common, n square times 2. So this is our expression. And this expression, this part is the common term, right? Now, this part, for this part, it's similar to that of kinetic energy. And for kinetic energy, what did we get? The value 13.6. So we substitute the same value over here times z square by n square. We have one more thing, 2 times 2, because the numerator 2, we didn't use it. So students, why did we multiply the numerator and the denominator? Just to make it similar to the kinetic energy expression so that the calculation is similar. Sorry, so that it's easy to remember the value. So minus 2 times 13.6 Z square by N square. This is the value for potential energy. So we have the value of kinetic energy. We have the value of potential energy. So can we find out the total energy now? So we have potential energy, we have the kinetic energy. So we can find out the total energy. Total energy will be potential energy plus kinetic energy. Okay, so potential energy is minus 2 times 13.6 Z square by N square. And the value of kinetic energy, the simplified version we got was 13.6 Z square by N square. So the total energy will be minus 13.6 times Z square by N square electron volt. So this is our total energy and it is negative. Okay, so the electron, if the electron is given, so electron has a negative charge and nucleus has a positive charge and the total energy is negative. So that means if the electron gets a charge or an energy equal to plus 13.6 eV, it can move out. Okay, so as long as it is, so this was the total energy of the electron in the nth shell. Okay, so you can calculate the different energies of electrons in different shells. So this is the expression. I'll just keep it like this. Suppose you have to calculate the total energy of electron in the first shell. So total energy. So can we just substitute the values? So 13 minus 13.6 times, suppose for hydrogen it is. So Z is 1 square by 1. So it gives minus 13.6 eV. So this electron, if it is given a energy plus 13.6 eV, it can move out. Similarly, you can calculate for n equal to 2. Total energy is equal to what? Minus 13.6 times Z square is 1. And this is 2 square, which comes to minus 3.4 eV. So if this electron is given a energy plus 3.4 eV, it can be removed. Okay. So students, if the electron is given for the second shell, if the electron is given an energy equal to plus 3.4 eV, the electron can be removed. Okay. Similarly, for the third shell, the total energy is minus 13.6 times 1 by 3 square, that's equal to 9, which comes to minus 1.51 eV. Okay. Then n is equal to 4. Minus 13.6 times 1 square by 16. Okay. That comes to minus 0.85 eV. So if you compare the energy of the electron in the first shell and the fourth shell, which one is more? So you can see that the energy is more in the fourth shell compared to the first shell, right? So energy is more in the fourth shell compared to the first shell. So that means as the electron is moving away from the nucleus, it's becoming more free. So energy of the electron is increasing, right? So students, we just saw that as the electron is moving away from the nucleus, the energy is increasing. The first shell, the energy is minimum, minus 13.6 electron volt. Second one, it is minus 3.4 eV. Third one is minus 1.5 eV. The next one is minus 0.85 eV. So you can see as the electron is moving away from the nucleus, it's becoming more and more free. So energy of the electron is increasing. Okay, so the total energy, the expression is minus 13.6 Z square by N square electron volt. This is the total energy. Okay, so if the electron is moving very, very far away, maybe N tends to infinity. Okay, so let's calculate the total energy. It will be minus 13.6 Z square by infinity. Anything divided by infinity will give you 0. So the total energy is 0. That means this electron is free from the nucleus. That means it has become free and ionization has taken place. Ionization has taken place. Spelling is wrong, sorry. Ionization has taken place. Okay, then one more last postulate of Bohr was that the electrons are revolving around the nucleus, yes. But if they get enough energy, they can jump to the next shell. They can accept energy and they can jump to higher energy level. Okay. Similarly, if they lose energy, they can recede back. They can come to the lower energy level. Okay. For example, if this is the first shell, it is this is the first shell, minus 13.6 electron volt. This is the second shell. This is minus 3.4 eV. Okay, this is the third shell, which is minus 1.5 eV, and so on. Okay, now if the electron is in the first shell and it is provided an energy of maybe positive 11 eV. Okay, so when you minus it, because obviously this minus sign will come, so minus 2.6 eV. Do you have any shell with this amount of energy? You don't have any shell. So this, even if you provide plus 11 energy, the electron will not move because none of the energy shell matches this energy. Okay, but if it is given an energy equal to plus 10.2 eV, okay, so you will get minus 3.4 eV. Is there a shell that matches with this energy level? Yes. So that means the second shell matches this energy level. So the electron can go to the next shell, next energy level, because it has the same energy as the shell has the same energy as the electron now. So it's not that the electron can go anywhere after gaining the energy. It should match with the orbitals also. Okay. Students, today we saw the Bohr model. Okay. In the next video, we will be talking about and we also talked about the different formulas. Okay, which are very important. You have to memorize all the formulas. All those formulas are shortcuts. okay, to do a lot of sums. In the next video, we will be learning about spectrum. Okay, that is yet another important topic. Okay, so that's all for today, student. Thank you. Have a great day.